So let me share whole screen. So I think last week or last time, Ben Arthur kind of showed some basic Julia code. I'm just going to go a little bit more into the compilation aspect and trying to show also some of the ahead of time compilation. So what is Julia? It's another open source general purpose programming language like Python. In particular, it has an emphasis on numerical processing. And kind of the intent of the language is it's kind of built from the ground up to be able to be compiled. And this makes it fast, but it also can add some latency because it tries to kind of hide the compile step so you don't have to explicitly do it, which is nice for someone coming from Python where you don't have this extra step. But it can also add some slowdown. And so I'm going to talk about how to maybe avoid some of that latency. So again, it's a compiled language. There's no discrete compilation step, but it typically compiles functions as you call them. And essentially, when the compilation does happen, that's a bad place for me to put this. And basically, it happens as you actually call the code, because this is when Julia can figure out what kind of actual machine types you're trying to use. So I'm going to switch over to a demo here. So this is kind of the thing as it's already cooked. I've already baked this in the oven. But as you can see, this came up pretty quickly, right? We just did popped up this GUI. And this is a simulation of a Gaussian beam. We're doing an optic simulation here. And you can see this is interactive. I can mess with a few parameters here. And you can see that this is being kind of computed in real time. I'm not pre-caching this, although there is some caching that goes as we compute, so it doesn't have to recompute what you're seeing. So that came up pretty quickly, and that's because I've already pre-compiled a shared library here. And sorry, I messed up the file extension. I'm running on Linux, obviously, here. But if I try to do that without that special pre-compiled code, native compiled code, you can see this actually takes quite a bit longer. And this is, I think, the main complaint about Julia is that there's this additional time to start up. And also, we want to get rid of that. But you see, it eventually came up. It just took a few seconds. Okay, but that few seconds can feel like an eternity to some people when you're just kind of waiting for it to happen. So I'm going to just get this other thing started, putting the thing in the oven, if you will. So we're going to use a package in Julia called package compiler. Basically, what this does is it replaces Julia's default native compiled shared library with something that you can create. So actually, let me bring this up over here just for a demonstration. So this is the Julia REPL. This is the package manager mode. I hit that by just putting a right-hand side square bracket. And I'm just showing you that this is kind of what I currently have in my environment. I'm going to activate the current environment here, which has a few more packages there. And so using package compiler, this is how you load a package in Julia. I'm going to invoke a method called create system image and pass a few keyword arguments. Basically, this is just going to just describe where I want to save my native code and also going to give a precompiled execution file. Basically, this is giving Julia an example workflow that it will use to kind of figure out what does it need to compile, and it's going to store that compilation into this shared library. So I'm going to start that process. It's going to take, I think, a few minutes to do, but we're going to continue the rest of the presentation and come back to this.
Mark?
Yes.
A very basic Julia question. What is that semicolon there?
Semicolon. So I think actually this is actually optional, but basically this separates positional arguments from keyword arguments.
Oh, okay.
So you can see all these things I've explicitly said, okay, the system image path argument is this string, GBLDOL, and the precompile execution file is this. But actually, this is optional. If you start putting things in this format, it will actually figure it out that these are supposed to be keyword arguments, but this is just doing it explicitly. So what's happening now is that it's starting kind of the analysis phase. It's actually bringing up the GUI. There's a few GDK assertion errors, but hopefully, where's the GUI? So, okay, I hope that worked. But basically, what it did was kind of it examined kind of what my workflow was, and basically what it needed, what it actually ended up compiling, and now it's going to actually try to recompile a standard library along with my code. Okay, so let's get back to the presentation. So in Julia, there's a few different kinds of compilation. There's something called pre-compilation, although this doesn't actually create native machine code. This just parses the code and figures out kind of what types are involved. What we typically think of a compilation is actually just-in-time compilation here. And this is where Julia actually compiles things in native code. And this usually is done as you go. And what I'm trying to demonstrate in my virtual machine here is ahead of time compilation. So this is basically your normal mode compilation when you're using something like C or C++. You compile all your code first, and then you execute it. Julia kind of upends this kind of workflow where it's basically trying to compile things as you go. And so it takes away that discrete stuff usually.
Another basic Julia question, and I know that this has been talked about before, but I totally forgot. Is it a strongly typed language, weakly typed language, or like inferred type or flexible type like Python?
It has a mix of both. And I'll get into that a little bit. So basically, by the time it's just compiled, it's strongly typed, okay? But it has multi-methods where basically it can take a weakly typed function and make strongly typed functions out of it. That's kind of the magic of Julia a little bit, is that it allows you to do that.
Is that kind of like templates in C++? There's something behind the scenes saying, hey, generalize this to all this whole set of types?
Exactly. And beyond C++, there's something called multiple dispatch, which means that as you give you can define different methods based on the different types of all the arguments. So I have a little bit of a demo for that. Just before we get into that, just a little bit about what's compiler. So mainly Julia uses something behind the scenes called LLVM. This originally stood for low-level virtual machine. If you use Java, you may be familiar with Java virtual machine. This is a little bit different in structure. For LLVM, what it does, it first compiles the code to an independent machine readable form. If you use Java, you might think of this as the .class files, which we have a Java bytecode. However, that in LLVM, that's never meant to be actually stored. Instead, this is just an intermediate form, which it can then compile that to different native code instructions for a specific processor. Okay, so let's look at pre-compilation first. So what I'm going to do is going to take some code. I'm just going to change a variable here, save it. And that's going to basically validate the pre-compilation cache. It's going to tell Julia that I've changed something, we need to recompile the function. And so I'm going to start Julia here, and I'm going to say I want to load my package. And now it's doing a little bit of pre-compilation. It took half a second to a second. But basically, what that did was kind of did a little bit of initial parsing of my code here. And but it didn't actually compile that natively. And it's not going to do that until I actually call or invoke any of the functions. However, I did give it a hint here, which is that I have two functions here. And you can see here that I haven't really typed any of the arguments here, Greg, right? So this looks pretty much like Python in terms of types, or typical Python, right? But what I did down here is I gave it a hint that the arguments I'm going to pass this function are int 64. So I'm being very specific here that these are 64-bit integers. You can be, but if you wanted to type things, I could be a little bit less specific. I could say integer here or things like this, or I could say be very specific and say int 64. So basically there's a whole sliding scale between strictly typed and kind of weakly typed. Okay. And
These
so
pre-compile functions at the end, this kind of
Yeah.
looks like a header file in C or C++. You're telling the
not,
compiler ahead of time like what the function signatures are.
yeah, so a header file kind of defines the interface, right? So it's just like that line, right? What this is actually just a hint to Julia that actually that you should expect these types, you know, when you're actually using it, and maybe start preparing code for that, right? You know, it would be perfectly valid for me to change all these to floats as well, right? And say you should also anticipate float input and prepare kind of that code.
Oh, so you could have more than one of these pre-compiles for a function.
Yes,
Okay.
because you see here, right? You know, here I could just say this is going to be some kind of number, and you know this will still run, right? So the nice thing is like C++, you can kind of reuse functions for different types, and similar to Python, you don't really have to think about types from the get-go, but you can kind of now reuse the same function with whatever you put in, and Julia will compile a distinct version for each of those. So let's just do a little bit of a demo here. So let's just have a very simple function. We have a and b arguments, and we're going to just compute a plus 2b. And if we run that, it's going to give us 13. Oops. Sorry, that's got ahead of me. Okay, so kind of the first step here is it lowers the code. So what that means is that basically it takes your raw code here, you know, just a plus 2b, and turns it into something that's a little bit more easy for it to think about in terms as a machine. So basically it says the first step is take b multiplied by 2, put that in a result %1 here, and then next thing is take that and add a to it, and put that in result 2, and then return result 2. Okay, so this basically lowers your kind of the code that you write into something that's a little bit easier for the machine to think about in terms of discrete steps. This is the first step in compilation. The second step is we need to now type the code. Okay, so you can see when I'm asking for this, I'm actually giving some real arguments. And in this case, I put in 3 and 5, and basically, so Julia is like, oh, these are integers, and so I'm now going to specialize this code for int64s. Okay, oops, sorry. I'm clicking. I have a tendency to click on things, and my slide presentation is not amenable to that. Where was I? Okay, so there's this. There's also kind of another mode here that's more for debugging, which is it also gives you extra information of how to interpret your argument. So in this case, it says, oh, okay, A and B are int64s, and there's this. So if I can give maybe a slightly different example, so this is what it looks like in the REPL. And let's see, so I think what I wanted to do was give an example of something that's a little bit more ambiguous. So so this is kind of bad function. It's a little bit harder for Julia to interpret. If basically A and B are odd, then it's going to return nothing, which is another type that's not an integer. Otherwise, it's going to run our original function. And now here, you can see that it's giving me a little warning in yellow that something's a little bit strange. It doesn't know what my return type is. It doesn't know that it's going to be an int64, rather it could be a nothing or int64. And this makes downstream compilation harder because now Julia has to think about, well, this could be an int coming back from this function, or it could be of type nothing. So that's kind of what that tool is for. If you can go down further through the tree, next step is compiled to LLVM, intermediate representation. And this is what this looks like. It's basically kind of really similar to what we just saw. It's getting less and less readable as we kind of go forward here. But but basically this is just this is just a shift operation. This is basically, since I multiply by 2, it's just shifting the bits over by 1, and then it's just adding the numbers together like we just saw. Okay, and so this is kind of a pseudo machine code. This is machine code that's not specific to Intel or your M1 chip or your ARM chip in your phone. This is kind of generic code. And the whole idea about the LLVM compilation framework is that it compiles everything to this form first, well, most things, and then from this form, it then will compile to native code that your Intel processor actually speaks. So if we look at this, we can use this code native macro, and now we have x86-64 assembly right here, right? And so this is kind of the steps that Julia is doing behind the scenes when you just run F3, 5. And so the problem typically is that this takes time to do. For a small function like F here, this is not noticeable, but for much larger code bases, there's an initial lag the first time you run the code. And so that's what I'm trying to address kind of in my demo. And to do that, we're going to do ahead of time compilation, which again is a typical compilation mode when you're using C or C++. Basically, there's a package by one of the Julia developers called package compiler. Basically, we still need to infer the types. So we need to get kind of given an example script to execute. But basically, it's going to monitor that script, figure out what we actually needed to compile, and then put that into a shared library, such as a DLL or a shared object. So let's see how we are doing. If I need to finish my okay, so basically it took about 6 minutes to compile this. And let's see, so I put it into a DLL. So there's a GBL.dl. Okay, and oops, that's not what I wanted to do. So, okay, in the end, since it compiled also the Julia standard library together with this, we ended up with 390 megabyte piece of code here. But this replaces kind of about 300 megabyte shared library that Julia would typically use by default, which is pre-compiled for you. And then we can just do the thing that we did in the beginning, which is just passing that in to Julia like that. This is actually going to bring up the REPL, but I'm going to include my GUI script, and this thing pops up pretty instantaneously because we've already done all the compilation hard work ahead of time. So that's how you can kind of get rid of that initial lag that we saw when I was trying to run this without creating a DLL. So there's our demo. My code is up here. This is originally a simulation that was written by Raghav Shetty, and if you kind of look at his version of repository, he's kind of complaining that I think at least in one version of this, it took minutes to basically get going with one of the GUI frameworks that he was using. But otherwise, it's not that long a piece of code. It's actually multi-threaded through different C planes using kind of a little bit of math optimization. But the threading is pretty simple. I just added this threads macro in front of my for loop, and this is now truly multi-threaded, not multi-processed. And so that's pretty easy to do. And I think the GUI here, we're using GTK. And this is I just separated my GUI code into some separate functions. But basically using all that, I think we got a pretty nice product. And actually, I think I had another slide. That's you can see I'm generating this from Markdown, so I don't know why it's not showing up. But basically, let me try that one more time. Okay, so there's a few other forms of compilation. So, oops, I'm really sorry about that. So one is a kind of GPU compiler. So LLVM can also be used to generate GPU code. In fact, I think most of the GPUs out there currently use LLVM behind the scenes to do that, to either compile CUDA or whatnot. And so basically, Julia just hijacks that framework to do compilation to GPU, so you can create GPU-based kernels. Something that we like is, you can see I created this massive DLL when creating my application. And so there's an effort to kind of borrow from some of the compilation for GPUs to make kind of smaller DLLs, for specific functions. The main issue here is with linking, trying to figure out how different pieces of stored code are supposed to relate to each other. And then kind of the last thing I'm going to point out, there's also, we can use LLVM to compile to WebAssembly. And so there's an example there of Julia running in your browser, which is kind of fun. I think what's the Python equivalent? There's a Python iodide or something like this that can be basically the same concept.
I have a question about the static compiling, really quick. So you were giving the compiled Gaussian beam application the DLL extension, referring to it as a dynamically linked library or as a DLL. But like you said, it includes the Julia standard library inside of it, right?
Yeah.
So why, and then you mentioned here that there's efforts to create a static compiler where, for example, you would only compile your application that then just dynamically links to the Julia standard library, which is installed in some standard location. Why call the first thing a DLL if it really includes everything?
Well, because you can load that dynamically into something else. So, and actually, if I did something else, and maybe I'll do this another how-to, is I can create a Julia function that's callable as a C function. And then I could go in Python, load C types, and use C types to call this Julia function directly from the DLL.
Okay, so it's referring to its use as being grabbed from other things. So, okay, cool.
So what's currently missing is a way to link. So let's say, preferably what we would like, and this is kind of getting in my wish list, is we want this to be faster, but also smaller. We don't want to drag around 390 megabytes around, although that's actually dragging around everything. And if you think of kind of all the other libraries you need for a basic C program, we often have a lot of other things going on. But what we really like is for my application to be compiled to its own DLL, and then it's also sitting next to the standard Julia DLL. And maybe you just load those two, and then everything works. There's several issues. I think what's happening in Julia actually ends up being a lot of recompilation, because as you add new methods, basically that invalidates previously compiled code, because now you've added more code that could be invoked, and basically ends up having to recompile old code. So it's kind of, where do you put that? How do you register that? And basically, there's also kind of, so potentially dynamic code generation, right? You didn't necessarily compile everything ahead of time, so you still be allowed to do that as you go forward. But those are things that are solvable. We just have to figure out kind of what is the user interface to do that. And so I think if you look through, say, the PRs for static compiler, you can, I think you can see some examples of people kind of going through and adding different interfaces to kind of slowly, incrementally make this thing work, right? So, for example, so using static compiler, we can create this function that figures out Fibonacci numbers, and then he's just doing this to kind of pre-compile it. But eventually, I think he gets to the point where he can store that compilation into a small file. You can reload that in, and then the function works. So basically, those efforts are underway. You can see that this is 13 days ago now. It's incrementally getting better and better. And it's basically based on prior work that that Julia already does in the GPU, which basically already fully functions in this manner. in order to run the GPU. So this is just now porting that back to the CPU. I think that's about it. Yeah, I think we just covered everything. So there's kind of your tutorial on a small GUI simulation plus GUI running it in your Julia, and how to make that faster and get rid of that first time to plot problem that typically plagues Julia.
Yeah, awesome. Thanks, Mark. I really liked those macros that showed the steps of the compilation. That was very enlightening, not just for Julia,
Yeah.
but for compiling code, period.
I've learned actually so much like about compilation and machine assembly from that. Because you can, as you can see, I took a very simple function and and basically I can see how that maps to actually machine code. And then I can make small changes to it, and it will show me how the machine code changes. That's something I've never been able to do.
I think
in other language, I think I need a lot of specialized tools to do it.
Yeah.
C, right.
I really I remember when I first started learning programming of any kind, it was still a mystery to me, like just writing Perl code, like what's actually happening on the CPU. I type in print, what the heck does that mean to a computer? And actually seeing it get reduced in a stepwise manner to a series of bit operations kind of helps you see that, like, all right, yeah, it's just logic all the way down.
Right.
And you can see all the steps.
Yeah, so I think something, right, you kind of might want to think about is, well, how come we can't just compile Python, right? What is this, the code I showed you doesn't look that different. And, I think part of it is a little bit of the semantics of Python, right? I think you typically use an int, but you don't really specify this is a 64-bit integer, but as you can see with Numba, if you specify that, right, you actually can compile the code, right?
I think that's by design. Like, I think it's good to have a language that isn't compiled by design, because it's just easier for people to jump into and start learning how to use. Like, I think that's the biggest hurdle for learning like C++ or a more like weighty, semantically verbose language where you have to specify everything. I mean, in C, then you have to memory manage everything yourself. It's too much engineering overhead for people who just want to solve problems quickly. So Python, it teaches bad habits when it's your first language. I mean, that's true for me too. But at the same time, it makes programming so much more accessible.
Yeah, and I think Julia's trying to cut the difference, basically, right? Basically, it's something that you can kind of use like Python, and it works. It's maybe not as fast as it could be, and you do a little bit more, it will get faster, and can get quite as fast actually. And so it's kind of in between, the missing link, perhaps.